He likes to have specified seats so he knows which students are sitting in which seats. So like if he needs to identify you, he can look at this chart and be like, that's who you are. And also, I think there's been some like studies done basically that if you do assigned seating, it's actually faster for students to get into their seats. So like it takes less time and then they can distribute the test more easily. So
I thought it was because like they thought that they was cheating.
no, they're not. I don't think he's specifically trying to separate anyone. He's just trying to know where people are and make it easy for everyone to efficiently get seated. Because it does take a while in some classrooms. It could also be a cheating prevention tactic, though, just because like you can't sit next to someone that you know necessarily unless you happen to just get placed next to them. So it probably also has that intended effect. Oh yeah, he did when I was a student. I had him as a professor of Math 22A in the year, I think it was 2000, and he was old then.
2000.
Yeah, I was a student here from 1998 to 2003.
Yeah.
And
To believe.
it's not that hard to believe. Yeah, he's been around for a while. Let's see here.
But then he writes the correct day.
I think he's pushing 80.
Doing that, we're trying to put serious.
I'm supposed to, that's not what I meant to do.
Like my freshman year was pretty young. My sophomore was pretty young. It was like my senior year.
Still looks to draw. I have this Sandy. That's the question. He literally wrote. He loves his father. He loves great.
Who doesn't have a test today? Who already took a test today? Who still has to take a test? All right. Well, we're not going to cover anything that's going to be on your test because some people have already taken the test. And also, we should continue on. So I totally understand if some of you that have a test coming up might want to mentally check out, but also this stuff is going to be on your next exam.
Yeah, next exam like 2 to 3 weeks.
Right, exactly. They don't stop in the Dallas class. They just keep coming. So, I will also point out this next topic usually gets most people do cover it. So even if you're not in the Dallas class, you should still pay attention because I'm pretty sure the other instructor will most likely cover this topic. I could be wrong though, so don't hold me to that. If you don't end up covering it, still worthwhile. Pens. Okay, cool. Where's my notes? I forgot to print them out. Let's see here. 1 second. Let's do that. Let's pin that. Okay, so sorry, get out of the way. There we go. You can see, okay, cool. Let's see. So my pen looks so weird. The class is Co-17B. Sorry, what's that? And today is what, November 3rd? Yeah. I know what I want to say. Before we get started, I did want to mention that Co-17, oh, I did a weird, sorry, I just hit a weird button on my computer and now I don't know how to undo that. Super annoying. Sorry, one moment, I'm having issues. There we go. Okay, cool. Let's see here. Let's double check just to make sure. Next quarter there will be a Co-17C class. I just want to let you know when it will be so that you can try to schedule around it if you care to. You obviously don't have to. You can still get added to Canvas if the time works for you or doesn't. But in case you're trying to actually come in person, let's see, is it actually posted on our website yet? Fall. Sorry, 1 second. There's always so much stuff here. And it's hard to see on my smaller screen here. I guess not. Is it not on here? Seems weird. Sorry. Oh, there we go. Cool. Okay. So just so you all can see it. Here's so winter pre and co classes. We have co classes. Co-17C will be Monday, Wednesday, Friday, same time, 1 to 2. It will be over in Boehner though, not in this classroom. So yeah. And there's the CRN if you want to write it down. I'll also post a Canvas announcement just so you can see it later. But it's also on our website. So if you go to the AATC website, you can find it there as well. Cool. That's all I wanted to mention. So today we will talk about first order linear differential equations and how to solve them. So first order linear differential equations, often abbreviated as FOLDE. So the first thing to know about a first order linear differential equation, other than it has a first derivative of your function and the function itself raised to the first power, there's a very specific way we want to write it so that we can deal with it. So here is the standard way of writing a first order linear differential equation. So standard. Here's the standard way of doing it. We write it as the derivative of your function plus some multiple of your function equal to some function of your other variable. So y is your function. It might be multiplied by some function of t, and then being added to y prime equal to some other function of t. So this is the standard way of writing it. So before you can do any of the stuff we're about to do for any first order linear differential equation, if you have something that's first order linear, but it's not written precisely this way, your job is to manipulate it first to make sure it looks like y prime plus something times y equal to some other function of t or x, typically are your independent variables here. So I don't love jumping straight to the solution, even though we'll come back to this. We're just going to work through a problem. Ooh, we could do that one. But let's work through the standard one first. So example, we want to solve the differential equation y prime is equal to t minus 3 times y. And I'll point out, and this is kind of the reason we're talking about this at all, is that this differential equation is not separable. You cannot write this right-hand side as something with as a function of y times a function of y. Sorry, a function of t times a function of y. Can't be done, right? You're always going to have t's and y's together if you try to write this as multiplication. So, right, this cannot be separated. The y's and the t's will be stuck together if you try to do that. So instead, we're going to rewrite it in this format where you have y prime. So we're going to bring the 3y, the minus 3y over to the left-hand side. So we're first going to rewrite in the standard format. That's what I meant. The standard format was the other word I'm looking for. That's what I meant right there. So first we're going to rewrite it. We're going to write it as y prime plus 3 times y equal to t. And not that it's super important to label these, but I'll just point out in this particular problem, the 3 here, that is your p of t function. It's not very exciting. It's just a constant, but it is a constant can be a function. And over here, here's your q of t. Sorry, I'm just thinking, I know the way that the other instructor, Professor Burke, or whatever her title is, I don't remember. She's not a professor, whatever. She likes to teach us a slightly different way. We'll talk about kind of both ways here, but we'll do it kind of the standard way first. So here's what we're going to do. Our goal is to multiply this whole equation by something and turn the left-hand side into the derivative of a product, which would require the use of the product rule. So please, if you have questions along the way, ask them. But here's what we're going to do. We're going to multiply both sides by e to the integral of p of t dt. This is usually either called mu of t. That's pretty standard. Some people use capital I of t, or whatever your variable is. This stands for the integrating factor. It is the thing we multiply by so that we can actually do the integration on both sides at some point. In this case, our e to the integral of p of t is pretty easy. It's going to be e to the integral of 3 dt, which is just e to the 3t. If you're in Burke's class, she does something slightly different where she kind of has you derive how you get to this in the first place, which we'll talk about in the next example. Yeah, there's kind of a little bit, yeah, we'll get there, I promise. So we're going to multiply everything by that. So our equation now is going to be, let's use another piece of paper. So multiplying by that, we get e to the 3t times y prime. It's also perfectly fine to write dy dt if you prefer, plus e to the 3t times 3 times y equal to t times e to the 3t. Okay, this will happen every time. The entire reason that we did this is now the left-hand side of this equation is the derivative of the product of two functions. Specifically, this right here is exactly the derivative of e to the 3t times the function y. I want to take a minute to let that sink in. So if we use the product rule here, it's the derivative of y times the other thing left alone, plus then you switch, it's the derivative of e to the 3t, which is using the chain rule, e to the 3t times 3 times the other function left alone. That's the whole reason we did this, so that the left-hand side looks like a very recognizable derivative of something. Okay, so now we're going to rewrite our equation as, how do I want to write this? Let me make sure I'm doing this not terribly. Sure, that's fine, yeah. We have that the derivative of e to the 3t times y is equal to t times e to the 3t. And now we get to make the next jump, which is that if you know, just like we were talking about, I think 2 classes ago, like if you know the derivative of y is equal to some function of x, you can just anti-differentiate that other function of x to solve that differential equation. I know it was a while ago, but we did do that. The same thing is true here. If you know that the derivative of whatever this is equal to that, then the inside part here has to be equal to the integral of this. So we get to say that e to the 3t times y is equal to the integral of t times e to the 3t dt. I'm pretty sure Dedel wants you to usually walk through this process when you solve these, even though there is kind of a shortcut to jumping straight to the solution, which we'll talk about in a second. The rest of this is just doing, feels like it's getting very weirdly dark and light in here because of I imagine the sun outside. The rest of this is actually doing the integral over here, which is going to require integration by parts and then dividing both sides by the e to the 3t here to actually solve it. So before we actually do this, I'm going to write one more thing. You can often write the final solution before you do the work as y equal to 1 over e to the 3t times the integral of t e to the 3t. Now be extra careful here. Don't be foolish like I was when I learned this the first time. The 1 over e to the 3t here and the e to the 3t there do not get to cancel out. You have to do this integration before you can start dividing that through. So let's see here. So for our integral here, we're going to do integration by parts. Where'd my purple pen go? There you go. So we're going to let u equal t. dv is going to be e to the 3t dt. Our du is 1 times dt. And our v is the antiderivative of e to the 3t, which is e to the 3t divided by 3. So then rewriting the whole thing, we end up getting y equal to 1 over e to the 3t times the integral of this, which is u times v. So t times e to the 3t over 3 minus the integral of v du, which is e to the 3t over 3 times dt. Well, that's not too terrible. Now we're just going to integrate this and we're going to get the following. We're still not going to multiply this through just yet. 1 over e to the 3t times, I'm going to rewrite this just slightly as 1/3 times t times e to the 3t minus the integral of e to the 3t divided by 3 is e to the 3t divided by 3 and another 3. So 9. And importantly, plus c inside these brackets, because this 1 over e to the 3t out here, or whatever the 1 over your thing is out here, has to multiply by the constant there. It is absolutely necessary. Let's see actually why here. Check this out. If we distribute this through, we're going to get y equal to, let's see, 1 over e to the 3t times 1/3 t e to the 3t. The e to the 3t's cancel. So you get 1/3 times t. And similarly, the 1 over e to the 3t times e to the 3t over 9, the e to the 3t's cancel, and you just get minus 1 over 9. And if you didn't have the c there, your answer would look kind of very boring, right? It wouldn't be really the function it's meant to be. We actually really need this part over here, the c that's getting divided by e to the 3t. Otherwise, your answer is really not correct. It's less of an interesting function than it should be. So, let me pause for a second. That's the general process for solving a first order linear differential equation. It's writing it in the standard form, multiplying both sides by the integrating factor, then writing the left-hand side as the derivative of a product, anti-differentiating both sides, and then actually doing the work anti-differentiating. It's kind of a lot of steps. Questions so far? Yes. P of t? Mm-hmm. So the y is just chilling there. So right there's y right there. So here's my. Oh, I'm sorry. Yes, of course. Thank you. So in fact, let's go back a little bit further here. So back here, here's my y prime plus p of t times y equal to q of t. And then in the next step, all I really did was I multiplied both sides of this equation by e to the 3t. So I have e to the 3t times y prime plus e to the 3t times my p of t right there, still just hanging out. Right there's p of t times y equal to t times e to the 3t. But the point is that in the next step, this 3 is kind of getting sucked up as being part of the derivative of e to the 3t. That's why we actually need this to work the way it does. And I'll do a more general explanation in a moment here. I want to see if there's anything else I want to say. No, I think that's kind of it. So the thing that's happening here, yeah, let's go a little more general. So here's how this is really working. Oh, I'm gonna say two things actually. So thing one, do I even really want to say this? Sometimes professors, probably neither of your instructors, neither Professor Burke or Instructor Burke, whatever their titles are, and Dr. Diddell, I guess he's a doctor. Dr. Burke is the right thing to call it. And Dr. Diddell, none of them, I think neither of them want you to just jump to the solution. But I'll point out it is sometimes acceptable to say, oh, the solution is always going to be the following. 1 over your integrating factor times the integral of your q of t times your integrating factor. I'm going to write that down up here for a second. So this next part, you are always welcome to write down, but you might just want to watch for a second. So in general, we're trying to do the following. We are trying to solve y prime plus p of t or p of x times y equal to q of t or q of x. All right, so we're actually going to do this one kind of the longer way, just to kind of also cover the thing that Dr. Burke usually talks about. So, oh, geez, we can pile on stuff over here. All right. Yes, and totally fine if you have an exam later this afternoon and you're like, I can't take this in right now. I totally get it. It's really okay if you want to leave. So we know we want the left-hand side to become the derivative of a product. So what we're actually going to do is we're just going to multiply by something, pretend like it works. So watch this for a minute. We're going to multiply both sides by a thing. I'm going to call it, I like to call it mu of t, but I feel like your professor likes to call it I of t. Oh well, such is life. So I'm multiplying both sides by this mu of t thing. And the thing that thing is supposed to do, its job is to make it so the left-hand side is the derivative of a product using the product rule. So this left-hand side should be exactly equal to the derivative of y prime times, well, sorry, not the derivative of y prime. Sorry, apologies. That's not what I meant to write there. Wish I had y that on me. It's supposed to be the derivative of the product of mu and y. It would have to be, right? Because to get mu times y prime here, it's the derivative of one piece times the not derivative of the other piece. And to get the other part right here, well, you've got y here, and then it's got to be the case that the derivative of mu of t is equal to mu of t times p of t. That's how that's getting derived. So we're actually going to write down that differential equation. So here's what we need on the side. I know it's so exciting. It actually is I think this is actually a really slick, smart, cool process kind of. So here's what we need. We need that the derivative of mu of t, we need the derivative of mu to equal mu times p. Let me show you what I mean here. I'm actually going to write this. So again, what we really have here, if we use the product rule, you think of this as like your f and your g, we have f prime times g plus f times g prime. This is supposed to end up being the same as this. And the only real difference is that part looks totally fine. Mu times y prime or y prime times mu. This right here, though, we've got the y, and then we need that the derivative of mu is equal to mu times p. That's what's happening here. That's where this is coming from. So that's what we're going to solve. And it's not terrible to solve at all. So we are going to separate variables. We're going to divide by mu and say 1 over mu times d mu. I can see why some people like to use I here. Is equal to p of t times dt. Now we're going to integrate both sides. The integral of 1 over something is, well, I should be careful. The integral of 1 over something to the first power. The integral of 1 over x or 1 over mu, that's going to be natural log of your something. I'm ignoring the absolute value here because it doesn't really matter. And on the other side, we just have the integral of p of t. Right? We don't know what p of t is, so we're just going to leave it like that for a second. And now look, we're going to e both sides, and we're going to get e to the natural log of mu, or just mu, is equal to e to the integral of p of t dt. So that's why that is the thing we multiply both sides by, because when you do, you exactly get that this other side here is the derivative needs to be. Okay, so just to show you all it really works, let me point out, if you take the derivative of this, the derivative of mu here, mu prime, well, what's the derivative of e to the something? It's e to the something times the derivative of the something. And the derivative of the integral of a function is just the function. Oh, look at that. The derivative of mu is exactly mu times p of t, which is exactly what we were saying we needed to happen to make this whole process work in the first place. It's kind of a lot to take in, but it really does work. And for those of you in Burke's class, I do think that she wants you to actually, so we'll do the next one kind of solving it like this, and then we'll talk about kind of the differences between these classes. So let's look at my next example here. Sure, we'll look at that. It's a good example. Okay, so let me not I have all the space down here. Yeah. Oh, sorry. There's more to say here. Apologies. Before we go to the next example. So then solving this, here's our solution. Because again, we're trying to find what? What are we generally trying to find? We're trying to find y, right? The function that we're trying to find, the solution is our function y. So here's what we have now. We have mu of t times y, and you can write mu with or without the t. Just like any function, you can write it with or without the input. The derivative of that is equal to mu of t times q of t. And then we anti-differentiate both sides. The antiderivative of the derivative just gives you the thing that's inside the derivative here. So anti-differentiating both sides leads to, on the left, just mu of t times y. On the right, the antiderivative of mu of t times q of t dt. Last step. We want to divide both sides and we want to solve for y. So we're going to get y equal to 1 over mu of t times the integral of mu of t times q of t. So what I was trying to say before was you don't actually have to go through this whole process of multiplying both sides by mu of t and then writing the left-hand side as a derivative of a product and then anti-differentiate both sides to get to this. You can say, hey, once I find mu of t, you can just jam it in here and say it's 1 over mu times the integral of mu times q. And you could totally do that if your instructor was cool with it, but they're probably not. So you should do it the long way. It's good practice. And these two instructors specifically, I'm fairly confident that neither of them is okay with you just jumping straight to this. Sorry. Okay, so let's do another one. So let's start with the following. Let me make sure I don't blow it. Bless you. So our equation is going to be, let's use x's instead of t's. X times y prime minus 4 times y equal to x to the 6th times e to the x squared. Let me just double check one thing, because I know I've done this problem before and I feel like I've gotten to a place where I'm making a mistake. And I think we're totally fine. Yeah, we should be good. Okay, cool. So first things first, it's not written in the standard way, right? We want to have y prime by itself. So if y prime is being multiplied by anything, you have to get rid of that. So we're going to divide both sides by x. So first step, rewrite it as y prime minus 4 over x times y equal to x to the 5th times e to the x squared. And I'm actually going to say one more thing here. This is fine, but if you're doing it the way we just did it, it's really easy to miss something important. If you were doing it the other way, you might accidentally say that p of x is equal to 4x. And it's not. P of x is equal to negative 4x. So I would encourage you to write, we're trying to write it as y prime plus y times p of x equal to q of x. It has to be a plus there, meaning we should really write this as y prime plus y times negative 4 over x equal to x to the 5th e to the negative x squared. I think this is always a good call, personally. I think if you have a minus sign here, you should trap that minus sign with the p of x or p of t part and always write it as plus y times whatever it needs to be multiplied by, so that you make sure you carry that negative sign with you. So the Dallas class, you would probably say my integrating factor is going to be e to the integral of negative 4 over x dx. We'll come back to that. Burke's class, you probably say, well, we're going to multiply both sides by something that's going to make the derivative of the left-hand side become a product rule derivative. We're just going to call it, I think she calls it I, so I'm going to call it I this time. So we're multiplying both sides by I. So I times y prime plus I times y times negative 4 over x equals I times x to the fifth times e to the x squared. And again, here's what the next jump we always get to make. The next jump is that this is supposed to be I times y prime plus I prime times y. Right? It's the derivative of a product. It's the derivative of the product I times y. So what that means for us specifically is you have to make this part match up, right? This part matches totally here, I times y prime, I times y prime. And here the y's are matching up, but we need the I prime here to equal I times negative 4 over x. It's the only option. Also, I'll point out the fact that it's a product rule might make it extra clear why it has to be a plus sign here. Why I'm not writing it as a minus sign, I'm sucking that up over there and saying, oh yeah, I need the addition here, so I do have a product rule derivative. So now here's what we're going to say. We need I prime to be equal to I times negative 4 over x. Okay, this is always going to be the same process if you have to do it this way in Dr. Burke's class. It's always going to be separation of variables. So your I prime is really your di dx it's where is it on the sheet? Thank you. Equal to I times negative 4 over x. And now we're going to separate the i's from the x's. I's on the left, 1 over I times di. X is on the right, negative 4 over x dx. Integrate both sides. Thanks, appreciate it. The left-hand side is always going to be a natural log. So the integral of 1 over I is going to be the natural log of I. On the other side, the integral of negative 4 over x, we can actually do it this time. And we're going to get negative 4 times the natural log of x. Now we need to be extra careful here. We're trying to solve for I. I would really rather not write I equals e to the negative 4 natural log of x. I'd rather first rewrite this side as the natural log of I equal to the natural log of x to the negative 4th, and then just say, oh yeah, I is going to be x to the negative 4th. Which I will point out is exactly the same thing you would get if you didn't do all this work, right? If you just did this integral here and you already knew the formula for the integrating factor, this is going to be e to the negative 4 natural log of x, and then the negative 4 comes up as the power, and you get exactly x to the negative 4th. The same thing, either way you slice it. But I am pretty confident that I remember that Dr. Burke wants you to show this work for finding your integrating factor if you're in Burke's class. Also, if I'm wrong, let me know. I think I'm right, but she could have done things differently this quarter. I don't know. Or she could eventually do things differently this quarter. So please, or Dr. Diddell, if he's all of a sudden like, no, it's totally fine if you just write the answer, let me know. I don't imagine that because he's an old man who's been doing it the same way for a long time, but he might change his mind. You never know. All right, so finishing this process, we're going to say, here's what we have. Our I is this. So we have the derivative of x to the negative 4th times y equal to x to the negative 4th times x to the 5th times e to the x squared. And then we're going to anti-differentiate both sides. This is the part I think people actually maybe get hung up on the most. We're just anti-differentiating both sides. And again, the antiderivative of the derivative of that thing there is just that thing there. So the antiderivative of the derivative of x to the 4th times, x to the negative 4th times y is just going to be x to the negative 4th times y. Now on the other side, it's going to be the antiderivative of this function here, which we definitely should simplify. The x to the negative 4th times x to the 5th is just x to the 1. So we get x to the 1 times e to the x squared. I'm going to write this next part in kind of a stupid way, but to exhibit a point. If we then solve for y before we do the integral over here, we end up getting y equal to 1 over x to the negative 4th, which I would never actually write, times the integral of x e to the x squared dx. And that's exactly the format that we talked about. It's 1 over your integrating factor times the integral of your integrating factor times your q of x. We just simplified it. I guess I could have written it like, I could have left it like that, but that seems absolutely terrible. It's a whole lot of work, depending on how much work you have to show. The rest of this is not too bad, except it's bad enough that I have to use another piece of paper. No. So we're going to rewrite this as y equal to x to the fourth. And then we're going to say over here, the integral of x e to the x squared, we're going to do a u substitution. We're going to let u equal x squared. Du is 2 times x times dx. So 1/2 times du is equal to x times dx. My integral comes back around and becomes the integral of, let's see, x dx is my 1/2 du, and e to the x squared is my e to the u. So that's going to be equal to 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. So that is what's going to be going right there. This is going to be x to the fourth times 1/2 e to the x squared plus c. I'm going to say it again because it's super important. I cannot stress enough how important the c is here. This might be the most important plus c in any of your integrating you've done so far. Because while another, like earlier on, we were just like anti-differentiating, getting like the function plus c, fine, the plus c was not that important. But here, it's really, really absolutely vital because this functional part out here has to distribute to both terms, including the c there. So our final solution is y equal to 1/2 times x to the fourth times e to the x squared plus c times x to the fourth. Questions about this so far? What else I have here? So most of the time, this kind of question comes up in what we generically kind of refer to as tank problems, where you have stuff going into a tank and stuff coming out of a tank. And not only do we have to first set up the differential equation, then we have to solve. So let's kind of do one of those. We have enough time, and then we should probably stop there because these problems are a bit lengthy. You might notice, in fact, actually, before I finish this problem, let's do one more thing. This is your general solution, right? We weren't given any sort of initial condition. But if we were given an initial condition, say like an initial condition of y of 1 equal to 15, then we could actually go back and plug in and figure out what the value of c actually is. So here, if I plug in 1 for x and 15 for y, it's going to be kind of gross. Oh, well, I made poor choices. So we're going to get 15 equal to 1/2 times 1 to the fourth times e to the 1 plus c times 1 to the fourth. So here, solving for c, it's not the prettiest, but c is going to be 15 minus e over 2. Which you then should plug back into your function to write your particular solution. So then we're going to say our particular solution is y equal to 1/2 x to the fourth e to the x squared plus 15 minus e over 2 times x to the fourth. A little bit weird, but okay. All right, let's talk about a tank problem. Yeah, I like tank problems. So here's typical setup for a tank problem. The typical setup is you got a tank full of some solution, and you're usually putting something into it at some concentration and some volume per minute, and then draining it at usually the same amount of fluid per minute, although it doesn't have to be, which makes it even more complicated. Let's do the less complicated one. So here's our problem. A large tank initially contains 100 gallons of solution that is 10% salt, meaning there's 10 gallons of salt in there. I don't love that. 10% salt. I'm going to change that. Because that's not a way to say that has 10 pounds of salt dissolved into it. You'll see why in a moment here. A salt solution with a concentration of 2 pounds per gallon flows into the tank at a rate of 5 gallons per minute. And importantly, this next part, these next words are important, although they don't really change anything, but they are important. And the well-stirred or well-mixed tank, it needs to be well-stirred or well-mixed so that what you're draining out has like a uniform concentration, right? You're not draining out the really salty part or the really not salty part. The well-stirred mixture is drained at the same rate of 5 gallons per minute. So that's not a question, that's a statement. So then the first question we're going to write is, write a differential equation that's modeling the system. So let's write a differential equation for how the amount of salt is changing. Okay, so here's what we usually do. We usually draw a picture. Here's my tank, and I've got 100 gallons in there, and it's got 10 pounds of salt. I said 10 pounds, right? Yeah. And then we're putting in 2 pounds per gallon at a rate of 5 gallons per minute. And then we're taking out 5 gallons per minute. Sorry, that's not the best picture I've ever drawn. So here's how we're going to set the differential equation. We're going to say that S of t is the amount of salt in the tank at time t. So fun side note, S of 0 is equal to 10 here. We didn't say we had an initial condition, but there is an initial condition. The amount of salt in the tank at time 0 is 10 pounds. So let's write on the side here. Oh yeah, S of 0 is 10. So here's how we're going to set the differential equation very generically. The rate of change of the amount of salt is equal to the rate in minus the rate out. Or how much salt is going in minus how much salt is going out every minute. Okay, so here's how we're going to write that as a differential equation. ds dt, the rate of change of the amount of salt, where S is the amount of salt. The rate in is usually pretty easy for these problems. We're putting in 5 gallons of solution every minute, and the solution has a concentration of 2 pounds per gallon. So we have our concentration, 2 pounds per gallon, multiplied by how fast it's going in, which is 5 gallons per minute. That's the easier part. It's your concentration times the rate your volume's going in. The draining part's always harder because the concentration going out is variable. In the beginning, the concentration going out is 10 pounds of salt per 100 gallons of volume. But as we add this salty solution, it's going to change the amount of salt, which is going to change the concentration. So we know, well, very broadly, the concentration of salt in the tank should be how much salt is in the tank divided by the volume of the tank. Just like the concentration going in was how much salt divided by the volume, 2 pounds per gallon. So here, the amount of salt in the tank is S of T, the amount of salt at any time T. And we're in a fortunate situation here where the volume of the tank is not changing. We're putting in 5 gallons every minute. We're also draining out 5 gallons every minute. So the net change in volume is 0. So our volume is 100 gallons. And then we're going to multiply by that concentration of salt in the tank by how fast we're draining it, which is again 5 gallons per minute. So this is the concentration going out, which is variable. This is the rate going out. This problem does get harder if the volume going in is different than the volume going out. Like if you're only draining 4 gallons per minute, this is a much more challenging first order linear differential equation to solve, but very doable still. All right, we should hurry up here because I'm running out of time. So let's rewrite this equation without all of the fanfare of units. We have ds dt equal to, let's see, 2 times 5 is 10. So we're adding 10 pounds of salt every minute minus s times 5 over 100, which reduces to s over 20. And I'm just going to write s instead of s of t. Now here's an interesting position to take. This differential equation is separable, but I don't recommend doing it that way for 2 reasons. One, the algebra is actually easier if you do the first order linear differential equation. 2, if we do encounter the harder version of this, where the volume going in is different than the volume going out, then you have to do it as a first order linear differential equation because it's not separable. So just an FYI. But I will point out, I'm going to rewrite this just slightly just to show you, you could, if you really wanted to, and maybe it's a good exercise on your own sometime, you could do this as a separable differential equation. Here's how you would do it that way. You would rewrite this right-hand side as one fraction. So I'd write it as ds dt equals, so I'd multiply this by 20 over 20 and get 200 minus s over 20. I would divide both sides by the 200 minus s and multiply both sides by the dt to get 1 over 200 minus s ds equal to 1 over 20 dt. And then you would integrate both sides and solve for s. It's fine doing it this way, but it's just, in fact, I'll tell you, I used to tell students it was better to do it this way first. But after doing it for a number of years, I was like, the algebra is just messier this way. The algebra is actually easier over here. The process takes a little bit more to learn, but once you've learned the process of doing it this way, I do think the algebra is nicer if we do it the way we did it before. So let's not do it this way. Instead, we'll do it as a first order linear differential equation using s instead of y. So here's our y prime or our s prime. Let's write it as s prime. We're going to bring this over here and write it as 1 over 20 times our function s equal to 10. Just to remind everybody what's going on here, our 10 is our q of t, our 1 over 20 is our p of t. I'm going to do this one the kind of shorter way where we just get to say what the integrating factor is. So here our integrating factor, mu of t, is going to equal e to the integral of p of t, so e to the integral of 1 over 20, which integrating that's really easy. It's just a constant, so you're going to get e to the t over 20, or 1 over 20 times t. Also, I should point out, when you're finding this integrating factor here, there's no plus c's to think about, right? You should never write plus c up here. You just not a thing. Also, if you ever have a natural log, don't worry about any absolute values here. Just ignore all the kind of extra pieces that we often would look at. So we're going to multiply both sides by e to the t over 20. So we're going to have e to the t over 20 times s prime plus e to the t over 20 times 1 over 20 times s equal to 10 times e to the t over 20. And look, this part right here, that's exactly the derivative of e to the t over 20, right? The derivative of e to the stuff is e to the stuff times the derivative of that stuff, and the derivative of t over 20 is exactly 1 over 20. So the entire left-hand side becomes the derivative of the product of e to the t over 20 times s it's equal to 10 e to the t over 20. And to differentiate both sides, the left-hand side, you just drop the prime. You get e to the t over 20 times the function s equal to the integral of 10 e to the t over 20. We're almost done. Integrating both sides, you're going to get e to the t over 20 times s of t. I'm going to start calling it s of t now, equal to the integral of this is really easy. When you integrate e to the something times t, you're just going to divide by that something. So we're going to get 10 e to the t over 20 divided by 1 over 20, which is multiplying by 20. So we're going to end up getting 200 e to the t over 20. Take a second to think about that. If you take the derivative of this, you would get 200 e to the t over 20 times 1 over 20, and the 200 over 20 would be 10. Oh yeah, that works out. Plus c. And then almost finally, we have s of t equal to this divided by e to the t over 20 is just 200 plus that divided by e to the t over 20. We're not quite done though, because then we have to use our initial condition to actually find the, and I should pause. The problem I said we were going to do was set up the differential equation, which we did do, and then I immediately started solving it. I should have said the next part of the problem was, and then we're going to solve, but it's pretty typical. So the last part here is to remember that we have s of t equal to 200 plus c e to the negative t over 20. And we also know that s of 0 is equal to 10. So plugging that in, we have 10 equal to 200 plus c times e to the 0. So solving for c is going to equal negative 190. So finally, we can say that the solution to this differential equation is 200 minus 190 e to the negative t over 20. And again, this is the amount of salt in the tank at time t. All right, that's all I've got. For those of you with an exam, good luck. For everybody else, I'll see you on Wednesday. And we'll probably talk more about this a little bit, depending on what people are saying about what we've seen in the class. So have a great rest of your day. Yes.
Question from the basics.
Sure.
Wait, so for
From my practice exam,
Yes.
or okay, sure, yeah. Either way, but yes. It's weird. Okay.
I want this last question that you went through.
Mhm.
So
Yeah.
P of 0, why is it P of 0?
Because, well, what does the problem say?
A patient's continually receiving drug through an IV drip if the drug is eliminated from the body over time. Oh, is it?
Continue.
So that the fraction that remains after T hours is e to the negative 0.3 T. At what constant rate should the drug be administered to maintain a fixed level? Oh, so.
Right, so
Zero?
specifically to maintain a fixed level of the drug in the bloodstream. So that means if we're starting with P naught in the bloodstream,
Oh, you wanted to stay.
we want it to always be P naught. So that's why we're saying that P of T is equal to P naught, because we want where P of T is the amount of drug in the bloodstream. We're saying, well, we want that to always be the amount we started with, which is P naught.
We want that to always be the same.
Yeah,
Okay.
That's why we do that.
Okay, perfect. Thank you so much.
You're welcome. You too.